In this second lecture video, we're going to talk about the impacts that tillage has on different soil properties, how those impacts on soil properties in turn influence cropping systems, and then we'll talk about the reverse flow of causality, how cropping systems impact tillage. Okay, so let's first start out with the impact that tillage has on bulk density, aggregate size, and distribution. So this is data from an Ontario experiment where they measured bulk density in the 5 to 10 centimeters and 15 to 20 centimeters of the soil profile. And they measured bulk density 4 to 6 weeks after planting, always in a corn, soy, wheat rotation. And they had a bunch of different tillage treatments. Let's just focus on what I would call the most intensive tillage or aggressive, which is the fall moldboard plow treatment versus the no-till treatment, just with row cleaners, just pushing the residue out of the seed row. So here we have bulk density. A couple of things to notice, right? Tillage reduces bulk density, right? More aggressive tillage reduces it more aggressively. No-till, you tend to get an increase in bulk density. That's especially true in the 5 to 10 centimeter layer, so the top of that soil profile. Once you get to the 15 to 20 centimeters of the soil profile or below that, the differences in bulk density aren't as great. Okay, so we have an increase in bulk density with reduced tillage or moving to lower, minimal till to no-till systems. What does that have to do with productivity or crop productivity? Well, a couple of things. Number one, denser soils with higher bulk density have root penetration resistance is greater. So roots have to spend more energy. That crop has to spend more energy growing those roots. Another example here is that moving from 1.1 grams per centimeter cubed bulk density to 1.4 grams per centimeter cubed bulk density reduces O2 diffusion by 91%. And that's important because roots need oxygen to respire. For them to function effectively, they need oxygen, and so low oxygen environments, they don't do as well. And so this is just an example. You can see in 1998, the 5 to 10 centimeter soil layer, that was approximately the type of change we were seeing in reduction in oxygen diffusion. Tillage also breaks down soil aggregates. That's intuitive enough to understand, it's breaking up the soil. And so it changes the distribution of soil aggregate sizes once tillage is done. And it typically shifts that distribution to the direction of smaller aggregate sizes. This is data from an Ontario experiment that basically just shows this. As a scientist, I'm a fan of data, and I just, want to show you some so you know where these conclusions are coming from. This is an Ontario study done in Centralia and Wyoming where they looked at different tillage as well as wheat straw management impacts on soil aggregates. So here you see the percentage of soil aggregates less than 5 millimeters in diameter. And with the fall moldboard plow, for example, with baled straw, about half of the soil aggregates were less than 5 millimeters and about half are greater. If you just go to the no-till, either baled or bare wheat residue management, you can see that it's about a third of the soil aggregates that are less than 5 millimeters in diameter. All right, so who cares if what tillage does to the distribution of soil aggregate sizes? Who cares if there's more aggregates less or greater than 5 millimeters? Well, a couple of points, a couple of impacts that aggregate size distribution can have. One would be preparation of the seed bed. So an ideal seed bed has basically a 50-50 ratio of micro to macro aggregates. So, aggregates that are smaller and greater than 2 millimeters in diameter. Aggregate size distribution will also affect soil organic carbon storage or soil organic matter storage. Soil organic carbon can be locked up and more resistant to mineralization in larger aggregates. So by breaking down aggregates, making them smaller, shifting that distribution via tillage, you're essentially reducing soil organic matter. You're promoting mineralization of that organic matter and release of nutrients. And so there's a balance between promoting mineralization on one hand and then retaining carbon in the soil for the other benefits that soil organic matter can provide. Finally, soil aggregate size is going to influence the speed of soil drying. So larger aggregates dry out more slowly than smaller aggregates. So by shifting that distribution towards smaller aggregates, tillage can effectively assist in soil drying, right? Making those smaller aggregates and they dry out quicker. So that's just off the top of my head, but aggregate size does have a number of different effects on cropping systems. Tillage also influences cropping systems through its impact on soil water status and availability. So it does this through 5 main pathways. Let's just talk about each one. So the most obvious one is that to the extent that tillage buries and incorporates residue, it will increase the erosivity of soil, right? Just by reducing residue cover. It's going to increase water erosion and surface runoff. It will also increase evaporation, again, because of that mulch effect that residue cover would have. So here's some photos, or a photo of runoff and basically water erosion on a field. I'm sure you've seen something like this in real life. Residue on the surface basically acts like a bunch of small dams, right? It obstructs the runoff flow path. It slows down the velocity of that runoff, so more of that water can infiltrate into the soil as opposed to just running off the field. Also, by slowing down that water, it reduces erosion, right? There's less soil particles that are in that runoff water, and it just reduces soil erosion. So tillage can increase the erosivity of soil to the extent that it buries and incorporates residue. The next way tillage influences soil water status is through its impact on pore size, pore distribution, and pore continuity or connectivity. So let's just define these terms before we keep going. Pore size refers to, the size of the pore. We typically talk in agriculture about macro and micropores. So macropores are pores with a diameter of 1 millimeter or greater, and micropores are pores with a diameter less than 1 millimeter, generally speaking. So why do we care about macropores and micropores? Well, they serve different functions in an agricultural system. So macropores, they are generally found between soil aggregates, between soil particles. They allow for very fast water infiltration. Water can move very quickly through macropores, but macropores cannot retain water. And I'll talk a little bit about why in a second. So microaggregates, in contrast, they do not let water pass through very quickly. But they can retain water via capillary action because the diameter is so small, and because of the adhesive forces between the water and the soil particle in those microaggregates. So micropores are generally found within soil aggregates. They're found in the aggregate themselves. So this is a 3D image of a macro aggregate. This is 5 millimeters in diameter. Obviously, you can't tell from this image. University of Guelph researchers did a 3D scan of this macro aggregate. And, 5 millimeters is big enough. You could pick it up and look at it, put it in the palm of your hand. It would look solid. But if you did a 3D scan, you would see that there was a couple of large macropores, so a couple of intra-aggregate macropores, but really a ton of micropores. I mean, if you look at that color image C, look at all those small micropores within that macro aggregate. And if this macro aggregate was placed in water, it would swell up to 40% of its size. It would increase in diameter by 40% because the water would go into the aggregate via the micropores, and the micropores would hold on to that water, and the macro aggregate would swell up as those pores got a little bit larger with the water. Okay, so this is the difference between micro and macro pores. let me just continue on. So we care about the distribution of pore size. So we'll talk about the ratio of micro to macro pores and how tillage affects that, and also the continuity of pores. So for pores to be effective, they have to be linked from, say, the soil surface down to 10, 15 centimeters below the soil, right? If you have a lot of macro pores, but they're only in the top 5 centimeters, there's no macro pores that go from the soil surface to 20 centimeters into the soil, you will not have very fast infiltration. And so the continuity of soil pores is very important for aeration and water infiltration. Not just the total amount of the pores, but how connected they are in that soil. Okay, so now that we know that most micropores are found within soil aggregates and most macropores are found between soil aggregates, we know that tillage reduces soil aggregates. It breaks them up. And if it does that, then you can suspect, or it's logical to think, that tillage is also going to increase soil porosity. It's going to create more macropores at the expense of micropores, and that change in the distribution towards macropores is going to increase total soil porosity, right? That's quite logical to think, and it seems to be correct. So this is data from a long-term tillage trial that Bill Dean, Professor Bill Dean, recently retired, has been in charge of. 25 years, this data was taken after 25 years of either continuous corn, 25 years of no-till or fall moldboard plow. And you can see here a statistically significant difference in soil porosity. Now, this is statistically significant. Is it biologically relevant? That's a different question. But there is definitely a statistical significance in the difference in porosity between moldboard plow and no-till after 25 years in continuous corn. And this is Bill's study, or Professor Dean's study, but this has been repeated in many other places, and it's basically the same conclusion that, in general, total porosity is going to be reduced in a minimum till or no-till systems compared to more aggressive tillage management. Now, there's a difference between porosity, which we've talked about, and connectivity. The connectivity of pores, which is very important, again, to make sure that there's a connection between the macropores at the surface, that they can bring water down deeper into the soil layers. And I think this is where no-till probably has an advantage, at least no-till over time. And so I'm going to show you some data. Again, I'm a scientist. I can't help but like data, but these are images. They're cool images, so it's not a lot of numbers. This is a cross-sectional image of the top 4 centimeters of a soil. This is a study done in Huron and Middlesex counties in Ontario. I really like it. What they did was, well, first let's look at the conventional tillage. So you can see this soil structure. Lots of large macropores due to the annual tillage, like we've been talking about. But what's interesting about this study is they did these cross-sectional images of a no-till field over time, over 11 years. And this is really what's interesting. So this is your conventional tilled soil. This is no-till after 4 years. And you can see a lot less macropores, a lot less voids in no-till soils, say the first 4 years or so. At the top, what's going on is you have these earthworm casts at the soil surface. And what this study found, and this was later verified in other studies in other parts of the world, was that it seems like earthworms are changing the pore size and distribution in no-till soils over time, okay? Because tillage can reduce earthworm population. So with no-till, you get higher earthworm populations in that field, and they are changing soil structure. So let's see what's going on. This is after 6 years. Okay, so you have more compressed earthworm casts at the top, but what you can see here is that we have more macropores now all of a sudden, these horizontally oriented pores, which are due to earthworms that are, burrowing horizontally, doing what earthworms do, just munching around, and creating these horizontal macropores in the soil. Very fascinating. So this is after 6 years. Now, after 11 years, look at that. This is the no-till field, 11 years. You have a lot more interconnected pores. You have a lot more voids. And what seems to be going on is that these earthworms are changing the structure of this no-till soil over time, increasing the macropores from an initial, very few macropores. And this has to do with earthworms. So we have a change in the distribution and size of pores, micro versus macro, in no-till systems over time. Now, this change over time, as I've mentioned before, seems to be this change over time in macropores in no-till systems seems to be due to the influence of earthworms. So this is earthworm number per meter squared at different slope positions in conventionally tilled or a no-till for 11-year system. And you can see significantly more earthworms in that no-till system. So no-till or minimum till systems seem to be more earthworm friendly, and those earthworms are creating macropores. Now, there's kind of an open question about whether pores are better connected in no-till versus conventional till. And again, pore connectivity or conductivity has a lot of is important for rapid water infiltration and aeration of the soil. You want pores to be connected so that water and air can infiltrate quickly from the top to the bottom or deeper into the soil profile. So this is a 3D image of a no-till soil and a conventionally tilled soil. You can see that there are more macropores in the conventionally tilled soil at the bottom CT, but it appears that in the no-till, these pores, there's less of them, but they're better connected. There's more connectivity. So I think overall it's fair to say that we're at the edge of our knowledge in terms of this question, how does tillage affect pore connectivity? The jury's still out because some other research finds that there is no difference or that pore connectivity is better in conventionally tilled soil. So I would say the jury's still out on that one. The third way that that tillage will influence soil water status and availability is through its impact on infiltration rates of rainfall. So generally, greater infiltration rates can reduce runoff, it reduces erosion. These are all good things. And if it brings water a little bit deeper into the soil profile, it can reduce evaporation. Because if that water just kind of stays in the top inch or two of the soil, it's more liable to just evaporate rather than be used by a crop. Okay, so this is data from a study that compared conventional to no-till infiltration rates. Infiltration rates here is centimeters of rainfall per hour. And you can see here the infiltration rate depended on tillage. It was generally higher in the NT or no-till, 3 times greater infiltration rate in dry soil. But it also depended on how wet the soil was when that infiltration measurement was taken. So basically, drier soils always had higher infiltration rates compared to wetter soils. That makes sense, right? Really wet soils, there's nowhere really for that rainfall to go, so you have lower infiltration rates. The authors attributed this greater infiltration in no-till due to less surface sealing because of greater residue on the surface, so less soil crusting, as well as greater pore connectivity in the no-till, so just more connected pores. Now, I will say that these kinds of studies, the infiltration rate in the conventional tilled field, that measurement depends on the time of measurement relative to the tillage pass. So in this particular study, they had fall chisel, I believe, and then spring secondary tillage. These measurements were taken in mid to late June. And so the timing of these measurements relative to tillage is going to influence the infiltration rates associated with conventional till. The fourth way that tillage influences soil moisture status and availability is through its impact on the distribution of aggregate sizes in that field. So like we talked about earlier, as tillage intensity declines, we get larger average aggregate sizes. The distribution of aggregate sizes in that field shifts larger average aggregates, and you can see that here. Now remember that 3D scan I showed you? That was a 3D scan of a macro aggregate, and we could see the micropores in that macro aggregate. All right, how's that for a tongue twister? But the point is that the macro aggregates have lots of micropores that will hold on to water. You know, that aggregate will swell up if it becomes wet, and it will dry slowly. And the larger the aggregate size is, the slower that drying process is. The fifth, well, at least for this lecture, the fifth and final way that tillage influences soil water availability is through its impact on root morphology. So obviously by availability, I mean that a crop rooting depth or rooting profile is going to influence, how much water is available to it. Deeper rooting crops can generally access more water. Okay, so root morphology, roots spend energy to grow, right? They need to push soil aggregates out of the way as they're growing, and that takes energy for the crop to do. And so they will not grow as deep as soil in strong soils. When you have very strong soils, root morphology will change. You won't have as deep roots. You'll have more root growth side to side, or horizontal root growth, rather than not vertical, but root growth at that 45-degree angle away from that crop. You'll have more side to side. So this is research that shows that in the top 15 centimeters of a no-till soil, you'll find 75% of the total root mass. Whereas in a conventionally tilled soil, you'll find only about 50% of the total root mass. And again, that has to do with the strength of the soil. What tillage does, no matter its purpose, is weaken the soil. And by weakening the soil, it allows for more deeper root growth. Okay, so we've had 5 different pathways by which tillage influenced soil moisture status and availability. The sum of these effects are, unsurprisingly, that soil is drier as tillage intensity increases in that system. And this is, again, more data just to show, this is Ontario data over the growing season, showing soil moisture content over the growing season, or I should say from April to early June. And unsurprisingly, no-till soils are wetter, slightly wetter, especially, say, in the late May and early June. That difference really starts to increase. Tillage also alters soil temperature, unsurprisingly. But the impact that tillage has on soil temperature depends on where you are in the soil profile. So here we have, this is temperature across no-till, chisel plow, conventional tillage. There's also air temperature at 3 different depths. You have 0.025 meters, which is 1 inch, 0.05 meters, which is 2 inches, and then 0.1 meters, which is 10 centimeters, or about 3 inches. And you can see that the effect that tillage has on temperature is highest at those shallower soil depths. So at the 1 and 2 inch depths, soil was much warmer in the conventional or chisel plowed system compared to no-till. But once you get to 3 inches or deeper, there's not a whole lot of temperature difference that tillage induces in soil temperature. The other thing to notice here is this diurnal fluctuation or pattern in soil temperatures, where in the top 1 inch or 2 inches, you get this increase in soil temperature during the day, and then it goes down at night. That effect is modulated. It's much more subtle at deeper soil depths. Another obvious impact that tillage has on cropping systems is that it alters soil residue cover. Okay, this is somewhat of a Captain Obvious statement, but again, I'm a scientist, I like data. This is another study from Ontario that shows you how residue cover is influenced by different tillage, and in this case, straw management systems. Unsurprisingly, with a fall moldboard plow, you have almost 0 residue, and with no-till, even if the straw is baled, with no-till system, you're getting 60% plus residue cover. Another way tillage impacts cropping systems is through its effect on erosion, wind and water erosion. So purely by burying and incorporating residue, tillage will increase wind and water erosion. This is a graph that shows this relationship very nicely. Basically, more residue cover, less erosion. right? We've talked about this earlier. Now, there's also something called tillage erosion, which is separate from wind and water erosion. This is a photo of it. It's basically the net downslope translocation of soil by tillage. It typically occurs when tillage is going parallel to a slope. So you can see here, this is a photo in Minnesota where basically the B horizon or subsoil is exposed, and the topsoil has moved down towards the bottom of that slope. You can see that black area there with the topsoil. Okay, so the rate of tillage erosion is going to depend on a number of factors. So the biggest one is probably how much tillage is occurring down the slope versus up the slope, because generally you're making alternate passes with the implement. It'll depend on the angle of the slope, the degree of slope, the type of tillage implement, when it's being done, etc. But here's a study that gives you a ballpark figure for net movement downward of topsoil due to tillage erosion. This is Ontario's study done at, I think, 2 or 3 different locations, different loam soils. They found that tillage erosion causes, on average, 26 kilograms per meter per year movement. So across 1 meter in every year, 26 kilograms of topsoil are moving down. So that gives you a bit of a ballpark range about how much tillage erosion is happening. So 26 kilograms of topsoil is not a lot in a square meter. I mean, it sounds like a lot, but over time, this can add up to a huge number. And so that is definitely something to watch out for. The next impact that tillage has on cropping systems is its impact on the soil biological environment. So we already talked about how tillage influences earthworm populations. The more tillage is reduced, the higher earthworm populations are. But they also affect the types of microbes that are in a soil. And it does so because it impacts aeration. So remember that in reduced till, no-till situations, we typically, at least initially, have much less macropores. And with less macropores, we have less aeration into those deeper parts of the soil. With less aeration, the soil environment is going to favor microbes that perform well in low oxygen anaerobic environments. It's going to favor those anaerobic microbes. Now keep in mind that denitrifying bacteria, those responsible for those harmful N2O emissions as well as just denitrification in general, those are also anaerobic bacteria. Tillage can also directly impact microbial populations through its destructive nature, By tilling, you're kind of destroying the little homes that the microbes made in the soil. And so you can get a decrease in microbial populations in that way. Look, I'm not saying that that's going to impact crop productivity, but that's what's going to happen to the soil microbes via tillage. So this is a really interesting data. I wanted to show you some data. This shows you the ratio of microbial populations in the no-till versus conventional with different soil depths. So for example, here you see total aerobes in the 0 to 7.5 centimeter depth, 1.35. That means that total aerobic microbial populations are 35% greater in no-till versus conventional till. If you look at NH4 oxidizers, that aerobic group, in the 0 to 15 centimeters, that's 0.89. And so that means that in no-till only has 89% of the NH4 oxidizers that conventional till has. So let's just look at the overall, don't worry too much about the numbers here, but on average, no-till will increase aerobic bacteria by 3% over conventional till in the top 15 centimeters. So you're not really impacting aerobic microbial groups, tillage versus no-till. But what you are increasing are the anaerobic bacteria. So in the 0 to 15 centimeters of the soil profile, no-till has 32% more anaerobic bacteria than conventional till, and 283% more denitrifying bacteria compared to conventional till. So you're really increasing the anaerobic microbial groups as tillage goes down. All right, we've been chatting for a while, and I'm sure it's you're getting hungry or something. So I'll just wrap it up here. Here are some other tillage effects on cropping systems. In terms of cropping system effects on tillage, here's a couple of questions to leave you with.